for all the virtual kids at home, the kids in class wanted me to make sure that you knew that I mismeasured this. This should be 2.5 in the first video, and that is longer than this one. They're still not congruent, but that was not measured correctly. So there you go. All right, so now we're going to go to section 5.2, and we're going to talk about things called points of concurrency. This is loaded with information, so if you have to rewatch the video or pause it, you might have to do that. Okay, it says when 3 or more lines intersect at a common point, the lines are called, this is a new word for you, concurrent. And you'll see this in your vocabulary. My handwriting is terrible today, I don't know why. C-O-N-C-U-R-R-E-N-T, concurrent. Concurrent lines, the best way to say this is if you ever enter a roundabout, which you're going to as you guys start driving, the roundabout, all those roads leading to the roundabout, when they hit each other into that roundabout, they're considered concurrent. So roads cross all the time. So this would be like 3 different roads coming into the same roundabout. Those are called concurrent lines. And then if you put a point right where they intersect, which is like the roundabout, that is called the point of concurrency, which goes with the fact that those are concurrent lines. So we call this the point of concurrency. So that is some vocabulary that we're going to be using. Okay, so triangles, since we're studying triangles still in chapter 5, triangles have 4 different points of concurrency. Each point of concurrency has its own unique features. So there are going to be things that you're expected to know about these points of concurrency. So we're going to go through them. All right, so this is the point of concurrency right here of the 3 perpendicular bisectors. So I want you to go over to the picture, and I want you to picture this line or segment as a perpendicular bisector. So see how it's making a right angle and a midpoint? So that's one perpendicular bisector. And then you've got more. So this is another perpendicular bisector. It's going to be making a right angle right here and a different midpoint. So double tick, double tick. And then you've got the third perpendicular bisector, which is going to be this one right here. And that one right there is going to make a right angle also, and then I'm going to triple tick. So what happens is when I make 3 perpendicular bisectors in one triangle, they are concurrent because they hit at a single point, and that point of concurrency has a name. So you have to know the name of where the 3 perpendicular bisectors intersect. So we're going to name that at the top, and it is going to be called the circumcenter. C-I-R-C-U-M-C-E-N-T-E-R. And there's going to be a reason why it has the word center there. So it's called the circumcenter. And it is the point of intersection of the 3 perpendicular bisectors. All right, now what happens is when you guys look at the different types of triangles, you're going to see on page 326 that the circumcenter can sit different places. So if you have an acute triangle, it's going to be inside the triangle. If you have an obtuse triangle, it's going to be outside the triangle. And if you have a right triangle, it's going to be on the triangle. So if you flip to page 326, it's going to show you an example of all 3 points of concurrency for perpendicular bisectors in an acute, obtuse, and right. So for the people in class, I will show you that. For the people at home, you're going to want to flip to page 326 and look at those 3 options of where it can sit. Okay, now once you have a circumcenter, there's something that's neat about it, which is why we study it. And that's because the circumcenter is going to be equidistant from something. So this is going to be kind of jammed full of stuff. But if you guys can take your circumcenter, and I want you to draw the segments to all 3 vertices. So you're going to connect the circumcenter to all 3 vertices. Now I did it in a bold blue marker so that you guys can see it. But these are the distances to the 3 vertices. And what's going to happen is those 3 distances will match anytime you have a circumcenter. So the circumcenter theorem says it is going to be equidistant. Remember, that means the same distance from the vertices of the triangle. And it doesn't matter which kind of triangle you have, acute, obtuse, or right, that circumcenter will always be equidistant from the 3 vertices. Okay, the other thing that's cool about the circumcenter is it's going to be the center of this great big circle that goes around the triangle. So you guys might have noticed that triangle on the outside. Notice that every single point of the triangle sits on that circle. So this circle is called circumscribed because it goes around the outside. And you guys know, like, circumference means around the outside of a circle. Circumference, that the first part of circumference is the same prefix as this. This is called a circumscribed circle. So the circumcenter is the center of the circumscribed circle, which means the circle's on the outside and the triangle's on the inside. Again, this is just a lot of information. It's not a lot of thinking, it's a lot of information, okay? All right, so that's one of the 4 points of concurrencies. So now what we're going to do is we're going to look at the second point of concurrency, which is when you do all the angle bisectors. So you're going to go to this picture right now, and you're going to look at the 3 angle bisectors. So I'll do them in different colors. So this is an angle bisector, so we're going to go arc, arc. So there's my first angle bisector. Then this is another angle bisector, so we're going to go double arc, because it's cutting that angle in half. And then for angle A, we have a third angle bisector, and I'm going to go triple arc, because we've cut that angle in half. Now, if you notice, all of those angle bisectors hit at one single point, which is a point of concurrency, and that's because those are lines hitting at like a roundabout. So those are concurrent lines hitting at a point of concurrency. Now, the angle bisectors don't hit at the circumcenter. It has a different name. It's called the end center. So the point of concurrency for the angle bisectors is the end center. And I'll tell you again why it has center in it, just like circumcenter had it in there. Okay, now, with your angle bisectors, notice I don't have a page number, and that's because if you bisect an angle, how could you ever go outside a triangle? Just picture this. Anytime you cut an angle in half, it has to stay inside a triangle. So the acute triangle, it's located inside the triangle. Obtuse, it's still located inside the triangle. And for a right triangle, it's still located inside the triangle. It's like it can't ever leave, and that's because you're bisecting angles, so you always are going to keep it inside, or it's always going to stay inside. All right, just like the circumcenter theorem that we had up here, we have something called an in-center theorem. So the in-center theorem is a little different because you are not going to be equidistant from the vertices this time. So I'm going to take my big fat blue marker, and I'm going to show you what you're equidistant from. So I'm going to sketch perpendicular segments to each side of the triangle. And it kind of makes like a little wheel in the middle. If you look, those 3 distances will end up matching each other. So your in-center is not equidistant from the vertices. Your in-center is equidistant from the sides of the triangle. So we're going to say that. The in-center of a triangle is equidistant from the sides of the triangle. Now, I made the blank a little longer, and that's because you've got to remember it's always the perpendicular distance. So when you're talking about distance this year, anytime you say a distance, it automatically is assumed that it's the perpendicular distance. Okay, now go up to the circumcenter. That was the center of the big circumscribed circle that went around the outside. So now look at the in-center. The in-center is the center of the inscribed circle. So the circle on the out or the inside is called inscribed. This triangle would be called circumscribed. It's around the outside. So this is the inscribed circle. So the in-center is the center of the inscribed circle. So let me say this again. The thing that's on the inside is called the inscribed thing. And the thing that's on the outside is called the circumscribed thing. So that's why these are like opposite from each other. All right, so flip your page over. So on the last 2, I'm going to go over the different types of segments you're going to have because you guys haven't learned these types before. This is called a median. So a median of a triangle is a segment with endpoints being a vertex and the midpoint of the opposite side. So I usually say M&M for this because I love candy, and M&M helps me remember that a median will go from a vertex to a midpoint. Okay, so I'm just going to kind of sketch one out to the side so you guys can see this. A median will go from a vertex to a midpoint of the opposite side. So that's what we're going to be studying, is what happens when we put three medians in a triangle. So down here, these are three medians. We don't have any circles, so you don't have to worry about the inscribed and circumscribed thing. But these are going to be medians, so check this out. My red median goes to the midpoint, so I'm going to tick, tick. And then my blue median goes to the midpoint, so I'm going to double tick and double tick. And then my green median goes to the midpoint, so I'm going to triple tick and triple tick. Now, notice that they are concurrent, just like the other two. And so we have a new name for that point of concurrency. This is going to be called a centroid. It's kind of alien sounding, but that is the intersection of the medians. Okay, now, if you guys have a centroid, you're going to notice that you always go to a midpoint. It will never go outside of the triangle, because how could you go to a midpoint and go outside? It's kind of like the angle bisectors. You can't go outside. So it always stays inside the triangle, inside the triangle, inside the triangle. It never goes outside. And of course, there's going to be a theorem that goes with it, which is why we study it. So the centroid of a triangle divides each median into two pieces. The piece from the vertex to the centroid is twice as long as from the centroid to the midpoint. This creates a 2-to-1 ratio. Okay, so let's go up here and I want to show you how this works. If this piece was 10 on my red median, then this piece would be 5, and the whole thing would be 15. Let's say I tell you on my blue median that the whole thing is 24. So what you have to do is think this piece is twice as big as this. So what you would do is divide it by 3. So 24 divided by 3 is 8. So this little piece would be 8, and this piece would be 16. It would be twice as big. So the piece from the vertex to the centroid is twice as big. And then we can do it with the green. Okay, let's say the little piece in the green, no, let's give you the big piece. Let's say the big piece was 28, make it easier. Then this little piece would be 14. So there's a 2-to-1 ratio when you have a centroid. The other thing is, if I took my centroid and I balanced it, I could hold it on my pen or pencil, and I would know that it is the center, what do I want to say here? Oh, balancing point. I think I was supposed to say in this blank, center of gravity. I didn't give you much room. It's the center of gravity. Oh, I have the center of, there. Duh. Center of gravity, or it can be called the balancing point. So if I hold it up, that actually is the point that it balances on. It's the center of gravity for a triangle in a triangular region. Okay, so the last one we're going to run through has to do with an altitude. And you guys might have heard of an altitude as the height of a triangle. So this is an altitude of a triangle, is a segment from a vertex to the line containing the opposite side, and it's going to be perpendicular to the line containing the opposite side. Okay, so I'm going to show you what a altitude looks like. You guys probably have seen a height of a triangle. This is the height of the triangle. It's the altitude. This is the height of the triangle. It's the altitude. This is the height of the triangle. It's the altitude. Now, notice that if your triangle is acute, the altitude's inside, right? If the triangle is obtuse, the altitude or the height of the triangle is outside. And if the triangle's a right triangle, it's pretty sweet. It's already one of the legs of the triangle, so it's on the triangle already. All right, of course, the altitudes have a point of concurrency. Why wouldn't they? Everybody else does. This is called the orthocenter. Now, it's not going to be the center of anything, because the orthocenter pretty much stinks. I feel bad for the orthocenter. He doesn't get a lot of pub because there's not a lot that goes on with him. So let's go down and look at the three altitudes in the picture. So let's take the first one. I'll make it in red. It's going to go from a vertex and be perpendicular. So there's one altitude. I'll make the second one in blue. It starts at a vertex and is going to be perpendicular to the other side. And then I'm going to make one in green. It starts at the vertex and is perpendicular. Okay, notice that those are concurrent and they meet at a point of concurrency right here. That is the orthocenter. Okay, great. Nothing much true about him, no theorem or anything, but he does have a characteristic about him that's kind of cool. So notice in an acute triangle, where do you think the orthocenter will end up being located? Well, the same as acute up here. It's going to be inside the triangle. Now, if it's an obtuse triangle and you turn this to an obtuse triangle, that orthocenter is going to end up going outside. So in an obtuse triangle, it will be outside the triangle. And then in a right triangle, you'll notice that if your altitude's one of the sides, the orthocenter is actually going to be on the triangle. And that's going to run my thing out. Ooh, Christmas color. Okay, so that orthocenter is not very cool. I usually say poor orthocenter because he doesn't have a theorem about him or anything, but he does have the characteristic of where it can be located. Okay, so you've got a lot of information, obviously. So what does this back page do for you? Well, it puts all the information together in one lovely document that has everything that we just talked about together with a couple of extra things down here that we'll go over. But these are all of the things that we just discussed, but it puts them all together in a compact form. So when you guys take your assessments over these, there's just a lot of information to process and to know, but there's not a lot of thinking, it's just remembering things. So use this page to help you remember that stuff.